Good day, everyone. So today we're going to go over Module 3C, which is isomerism. So we're going to continue on with what you typically think of in terms of isomers, in terms of constitutional isomers, so having the same molecular formula but different connectivity. We're going to kind of backtrack and just distinguish isomers, isomers versus conformers. So if you don't remember, conformers are really going to be a means of rotation as opposed to a difference in bond formation. So if you remember, for your conformers, like for instance, say dibromobutane, 2,3-dibromobutane, you're going to have, so this is going to be a high energy, relatively high energy conformer. Okay, so essentially the way the bond between C2 and C3, the way they rotate with their respective substituents attached, it's going to give you a better understanding of what kind of energetics there are with interacting with the different substituents that you have there. Now, isomers in a different, on a somewhat related topic, but completely different concept, or just different connectivities. Okay, so the first thing we're going to get into is chirality. So in other words, handedness of something that can't be superimposed from one side to the other. So in other words, my hands, my left and right, although they look like they are mirror images of one another, they close differently, or they close the same but in different directions, right? So this right hand doesn't flip in like how my left one would. Okay. Planes of symmetry, so there's no plane of symmetry within my hand, right? My thumb isn't the same length of my pinky, etc. Then we'll get into enantiomers, so in other words, chiral compounds that are mirror images of one another. So in other words, you may swap out one configuration per stereogenic carbon or stereocenter. Then we'll look at identifying different types of stereocenters and making sure whether or not they have some kind of optical activity with respect to plane polarized light, which we'll get into at the beginning of the next module. Then highest to lowest priorities to establish configuration. So for instance, bromine is going to be top priority because it has the highest molecular weight, followed by CH3, followed by this back carbon here, which has other things attached to it, like another bromo group, CH3. Third would be CH3, and then of course last by default would be hydrogen. Diastereomers, so compounds that have more than one stereocenter, okay, whether they're reactive or not. And then interpreting Fischer projections, which are essentially just two-dimensional sort of line drawings where you can deduce what that is relative to sort of a zigzag linear fashion like you've seen before. Okay, so like I said, just to recap, isomers versus conformers. This is not going to be the same as, say, this BR. So this is going to be the 4 carbons, 1 carbon, 2 carbon, 3 carbon, 4 carbon. Okay, so these bromo groups, how they're situated, may not be in the same kind of configuration like what you see right here. Okay, so, and then, if you, let's say, change those dashes to wedges, or one of those dashes to wedges, you wouldn't have the same compound. You would have an isomer between the two. These would actually be diastereomers to one another, but we'll get into some of these sort of definitions in a little bit. So let's begin by talking about chirality and handedness. Just sort of some general concept or sort of examples for you guys to think about. All right, so with chirality, I had my hands before. So again, there are mirror images of one another, but you know, if I were to try to put, let's say, a catcher's mitt that I would typically put on my left hand, if I tried to put that on my right, it's not going to fit very well, right? So therefore, I won't be able to really catch very well with my right hand, or maybe even put it on altogether, right? Same thing goes with, let's say, some kind of drug or substrate, right? So if it's R configured versus S configured, particular enzymes within metabolic pathway or something are not going to recognize that particular isomer, right? And therefore it may be inactive, or it may do something completely sort of bad, or something that would give some kind of negative reaction, right? So thalidomide is one of those examples. It's sort of a textbook example that they use even back in the day when I was going to take organic chemistry. You know, so it would give some kind of birth complications, or you know, some type of effect that you don't want. Okay, so you know, if you get some enantiomerically pure or some stereospecifically pure type of compound, you can get a better, more direct target in terms of what kind of molecule you're working with. So that's just sort of a pharmaceutical example there. It was kind of vague. All right, now think of a screw or a bolt. So a bolt or a screw is driven into a medium clockwise. So if I'm taking a drill, I'm driving it into, let's say if I was trying to drill this into the wall, probably not on the white part, but you know, where it's not visible, drill it in, you know, it's going to go in clockwise, right? But if I wanted to take that screw out, I'm not going to keep on continuing to drill clockwise. I'm going to have to drill counterclockwise, because that screw is actually spiraled in one particular direction, right? And just like if I had a bolt and I had some kind of nut to fasten it and to tighten it, again, I would need to have something that would fit along those lines to where, you know, I could actually tighten it, as opposed to if it were in another direction. You know, you could put it in one, you could fasten it on one way, but you probably couldn't fasten it on the other. Okay? So that's essentially what handedness is. So let's think of a few examples here. First being an electric guitar. So if I pick up a left-handed guitar and I try to start playing, you know, being right-handed, it's going to be pretty sloppy, right? Unless I have one of those, you know, one of those classic guitars, and I switch over the strings and I do what I need to do, right? So a classical guitar is going to look something like this. It's going to be an awesome looking guitar that they will put into the Smithsonian, because this is such a beautiful illustration of one. Okay, so you have your awesome 6 strings that are going down over there towards the bridge from the stock. Right. Okay, so you're going to have from lower to higher pitch strings. Again, they're going to be thicker to thinner. So that would be if it were to strum this way and you're right-handed. Okay, but seeing as there's a sort of a plane of symmetry about this particular guitar, even though I'm sure it's not drawn that way, I intended it to be. But if I were to flip around the strings, it wouldn't matter, right? I wouldn't have to buy a left-handed guitar. Okay, so an electric guitar is going to be a little bit different. So if you think of a guitar like this, you have to have a little, this is an electric guitar where you'd have to have more access towards the bottom where you could do leads. You know, you have some ugly headstock here that is really not representative of any type of classic model at all. We'll make this one a bass guitar, how's that? But it still has some kind of chirality, right? If you were to play a left-handed guitar, so this would be in a right-handed fashion, right? You have the pickups and what have you. You have your little knobs over here, okay? And if you were to play that left-handed, it would kind of look a little goofy, and of course the top strings wouldn't be heaviest or thickest, right? So it wouldn't have the lowest end. So you would have a kind of a switched over form in it, and it wouldn't be as comfortable to play. Okay. Another example would be a conch seashell. So these are some of the kind of things that you can see ornamentally. You can find them in, you know, some Asian markets and what have you, like a smaller conch shell. Let's take another example. So let's say a 2020 readout, since 2020 has been such an awesome year so far, right? So let's say if it's on a digital clock, if we had a mirror image of this particular four-digit sequence, would it look the same? No, actually it wouldn't. It would bring us back to the year 505, right? Assuming you were counting the zero there, a leading zero, right? So in other words, this would be a chiral number, if you will, I guess. And, you know, that would be a mirror image of 0505, even though they aren't exactly the same numbers at all, right? So there's a distinction. Okay, so I noticed that, or I was explaining to you that this has some kind of plane of symmetry within it. This does not, right? So an electric guitar is not going to have a plane of symmetry. An acoustic guitar, you know, if there's nothing cut out and there's symmetry on both sides, then yes, it's going to be a plane of symmetry vertically within it. Okay, there's not going to be a plane of symmetry horizontally, as you can see here. Okay, so ways of identifying chirality or plane of symmetry is by means of looking at a non-superimposable image. So if you flip it over, it's not going to be the exact same thing as what you see on the other side. And then that plane of symmetry is not going to be there. So let's say we have, so I had this one example here. Let me erase these beautiful guitars and timestamp that I have. So I have a bromo group wedged out, methyl group here, CH3. So put a hydrogen in the back with the dashes. And then we have this planar portion, which is just going to be in a carboxylic acid. Okay, so if we have a mirror image, let's just do a vertical dotted line there. So we have a mirror image, and we put a mirror image like what we see over here on the other side. Will it be the same molecule? Okay, one thing to make note of is something that's planar like this is going to be able to rotate anyway, right? So that's not really going to affect anything. But things that are in 3 dimensions, like what's branched off of this particular carbon, are what we're going to pay attention to. So let's say if you flip this over, what is that actually going to look like? It's actually going to look like So that hydrogen is going to stick out now. And then this bromine group is going to go into the plane of the board. Okay. So really what you're seeing here is you're seeing that there's an inversion of configuration, or there's a change in two particular nuclei or coordinates that are sticking off of that particular carbon that is three-dimensional. Again, it has a total of 4 coordinates branching off of it. So you have a hydrogen, carbon, bromine, and then that carboxylic acid moiety. Okay, so and there's simply chirality among these two compounds, right? So they are mirror images of one another, but they are not the same compound. Okay, there's no axis of symmetry here going horizontal, so we can rule that out as well. Okay, so in other words, these are non-superimposable. When I flip this over, this can't stack up directly over that and you know, cancel one another out. Okay, so let's now think of plane of symmetry here. I'll draw a couple of just hydrocarbon examples. Okay. So the first one going to have dimethyl cis, right, about that particular ring. So if it's sticking, both are sticking out, and there's clearly a plane of symmetry here, if I were to draw it perfectly, right? So it's going to go perfectly vertical up and down. So that means that there are stereocenters here, right? Because if we're looking, let's say if we were taking this particular line across, right? So we have 1, 2 carbons on the left, 1, 2 on the right, but then we have an additional methyl group hanging off of here. So there is no plane of symmetry right here. Same goes for this side, right? So in other words, these are chiral centers in an achiral compound overall, right? So if there is a plane of symmetry, and that within the compound, then that means these are said to be meso. Okay, so this is a meso compound. Okay, so the same thing could be said if we have a 1-3 relationship. And again, those two carbons are on the same side of the plane. In other words, wedging and sticking out. Okay, so we have that split down the middle. Again, there is a plane of symmetry here. But if we were to take this one side and flip it over, it's actually going to be sticking in as a dash, right? Not as a wedge. Because right now it's sticking out as a wedge. Okay, but if you flip it around 180, it's going to be going into the plane of the page. Same goes if you were to flip this vertically as well. But here is sort of the take home. This is also going to be a meso compound because that, again, there's a plane of symmetry right there. And both of these methyl groups are going to be sticking outward. Okay. Now, again, there's chiral centers in an achiral molecule. Okay, so this would look, just for the sake of argument, this is going to look the same as what I'm drawing right here. Right? All this is just flipped over. Right? Same goes with okay, so these are both the same compound. These are both the same compound. There's the same kind of connectivity with the methyl groups, and there is a plane of symmetry there. It's just flipped over in terms of perspective. Okay. So let's look at another example where there isn't a plane of symmetry. Now with this guy right here. Now if we flipped it over, would it look the same? Yeah, it would look the same. But here's the thing, is that there's just one carbon on this side, and then there are two carbons on this side if we're looking from either this carbon or this carbon. So in other words, we're always looking at sp3 hybridized carbons and trying to deduce whether they're going to be one sort of configuration versus another. And we'll get into R and S configurations here very shortly. But I want to continue this a little bit more. So in superimposable molecules, which have the same elements but different connectivity, about all stereocenters. So enantiomers, so these two compounds with respect to one another are going to be referred to as diastereomers. Okay. Between this compound below, which has anti, and this has a syn or cis configuration. Okay. So let's take a look at a couple of enantiomers. So in that previous example that I gave you with two bromo, two bromo and two methyl propanoic acid, you were seeing the mirror image. Those actually are enantiomers of one another. Okay, so what exactly am I talking about? Get on over to this side. Okay, so remember I had that bromo group wedged out here, which is really where you want it to be. Let's put a CH3 group here. And then again, if something's planar like this, you're not really concerned about the way it's going to be situated, whether the OH is going to be on this side or the CO double bond is going to be reversed, whatever. It doesn't really matter. What it does matter is what's three-dimensional here. So bromo is going to be sticking out of the plane of the page, right? So bromo is going to be first priority because it's around 80 Daltons, right? So bromo is going to be number 1. Number 2 is going to be this carboxylic acid. So we can really think of carbon being bound to one oxygen, two oxygens, and then a third oxygen. So for each bond that you see here, you have to represent it as singly bound when you start getting into tiebreakers, which we'll get into a little bit later when we get into nomenclature. But bromine's going to be first priority. This carboxylic acid. Remember, whatever is connected directly to this stereogenic carbon. Okay, and then third is going to be CH3 because that's going to be higher than hydrogen. So what you're going to be looking at is what's directly connected to that carbon center. Okay, so it should go 1, 2, 3. So if it's going in a counterclockwise direction, it is what is referred to as S, or sinister. So counter clockwise. And that means that it's going to be left-handed, right? So if you were to twist it with your left hand, that's what it would look like. So you're going 1, 2, 3. So, you know, a long time ago, they thought that left-handed people were, you know, sinister and demonic in some kind of way. Hey, whatever. Okay, so let's think of the other configuration. Now what we're going to do is we're going to swap our bromo wedge out with this CH3. We're just going to put the CH3 in regular line form. Okay. We can twist this if we want to. It really doesn't matter, right? Because again, we're primarily concerned with this particular carbon here, which is sp3. Okay, so bromo is going to be number 1. So the priorities aren't going to change no matter which configuration we have, right? So it's going to be number 1. This carbon's going to be number 2. This carbon's going to be number 3, and then de facto 4 is going to be the hydrogen. Now, when you're looking to deduce what kind of configuration you have to make sure that the top 3 or the highest priority elements or nuclei that are attached to that stereogenic carbon are facing outside, right? So this hydrogen is going to be going into the plane of the page. So this is going to go 1, 2, 3. So that's clockwise. So that's going to be R for rectus or right hand. So clockwise. Okay. So that's really the difference. So really all you're thinking about is substitute or taking 2 substituents and swapping out where they are spatially bound to that carbon relative to the other 2 things that are staying in place. Okay, so now we're going to take the opportunity to go over enantiomers versus diastereomers, and I'll show you the distinction here. We'll go over a few other examples, but especially when we get into Fisher projections. But let's start at a, let's say 1 or 2 stereo centers here. So this is going to actually have 2 different stereo centers. Reason being is that if we can switch not only the 2 substituents that are about this particular carbon, we can also switch this CH3 to be on the other side, right? And then have a lone pair on the opposite end. So just like we're seeing our E and Z configuration of alkenes, you can have the same sort of phenomenon here with a CN double bond, okay? So in other words, these are chiral compounds as well. The thing is that while these 2 substituents connected to the carbon are fixed in place, what's changing here is this particular position in which that CH3 group is branched off of the nitrogen, right, and where the lone pairs are. So these are not a mirror image of one another at all. If you were to flip this over, you're going to have these 2 swapped over. So in other words, these are going to be diastereomers of one another. So that means these species are just one particular stereo center changing out of multiple. Okay. Now there's just one stereo center here on the bottom quaternary amine example here. So the one just being about that nitrogen, that quaternary nitrogen there. Okay. Notice that it's also positively charged. So we have CH3 over here, we have an isopropyl group here, we have an ethyl group here. Okay, these are mirror images of one another, as ugly as I drew them, right? But you can see that you have 1, 2, 3, 4 different species hanging off of that nitrogen. So that's really the telltale sign that you have some kind of stereospecificity about a particular nucleus, right? So this would be your branching or central element, right? So, in other words, if we were to think again about whether something is R or S, backtrack here for a minute before we do that. We're still going with the same convention with higher to lower priority. So we would treat this CN just like we would treat CC, like you saw in the previous submodule. But the CH3 group is going to be higher priority than a lone pair, right? So this is going to be higher priority on this side. And then it's going to be opposite of a cyclobutyl group is clearly going to have higher priority than just a methyl group, right? Because you have a carbon and then two carbons branching off of it, wrap around a ring. Okay, so it's going to beat out with a tiebreaker of that those three hydrogens that are connected to this carbon. So in other words, highest priority, highest priority. If they're on the opposite sides, this is going to be an E isomer, okay? And then when both of these are on the same side or, you know, together, right, it's going to be a Z isomer. Okay, now in terms of priority here, which one is going to have highest priority? It's going to be this propyl group, followed by this ethyl group, followed by this methyl group. Okay, so here's a little bit of a trick here. Why is this in the back? Well, that's the thing, is that you always want to think of the highest, the top three priority coordinates about that stereocenter being in the front, okay? So with this hydrogen being there in the plane of the front, we're going to have to imagine things being sort of flipped, if you will. So let's draw our assignments here. This is going to be the first priority, this carbon here, followed by this number one spot of the ethyl, followed by methyl being 3. Okay. And then hydrogen is going to be the last. Okay, so if we were to, if we're looking at things by how they're depicted here, we're going to go 1, 2, 3. Now, if I were to make, let's say, a model, I'm going to do that, and I'm going to pause this for a minute, and we'll come right back, and I will show you that model. Okay, so here is the molecule that I have at the left. So this is going to be the isopropyl group that I'm kind of moving around. Maybe you made this already with your own. Okay, this is going to be the hydrogen that's going to be sticking up top. Then this is going to be the ethyl group. This is going to be on the left here. Then you're going to have the methyl in the back. Okay, so that's right here, just this one methyl group. Okay, so what we would do is we would just turn this around. So it doesn't matter how much all this stuff rotates, right? It's still going to be fixed in the same position. Okay, so isopropyl is going to be first, followed by ethyl, which is going to be second, followed by methyl, which is going to be third. So this is going to go 1, 2, 3. That is going to be sinister, so that means it's going to be in the S configuration or counterclockwise. Okay, so back to what we have two-dimensionally here. If it's going to go 1, 2, 3, if we were looking at it like it's, you know, as we're seeing it right now, we would just say, oh, hey, look, that's R. Well, not exactly, because this fourth priority isn't in the back. If you flip it over into the back, then it's going to switch, right? So in other words, you know, if you were just to keep track of this stuff on paper, you'd say, oh, well, that's cool. That's going to be R right there. I would put it in quotation marks because we know that this lowest priority, hydrogen needs to go into the back. So what you would do is rotate it to where this methyl group is going to go somewhere around this triad. So in other words, it's really going to be S. Okay. Now, let's just take two. Let's just make it less messy. So let's take the ethyl group and the methyl group and swap them up. Just change the connectivity here. Okay, so what do we see here? We see pretty much the representation what we have on the right now. Okay, so we have this highest priority propyl isopropyl group, second highest priority, which is the ethyl group, and then the methyl in the back. Again, you want that to where you want it to look like the lowest priority is going to be sticking in the back to figure out what the proper configuration is. So it's going to go isopropyl, ethyl, methyl. So that is going to be R. Not surprising because it's going to be the enantiomer of your S-configured molecule here. So once again, looking at things two-dimensionally, it's going to go 1, 2, 3, which is, we look at it and as it appears looks like S, but again we need to flip it because that hydrogen is in the wrong side of the plane. So it's really going to be R. So this is going to be S, this is going to be R, just one stereo center that's being inverted. So in other words, these are S and R enantiomers of one another. Okay, so one thing to deduce diastereomers from enantiomers is that if you flip all of the stereocenters, let's say if you have 2 or 5 or 8, right? If all of them are inverted, that means those two compounds are enantiomers of one another. So enantiomers mean all stereocenters must be inverted. So diastereomers are one or more, but not all of the stereocenters inverted. Okay, so that's the distinction. All right, so this next segment is what is referred to as priority and tiebreakers. So in your notes, I have this particular compound. So D is up top. So D is for deuterium. So deuterium is just heavy hydrogen. So it's just hydrogen with 2 atomic mass units. So an extra neutron. So this will be deuterated ethylamine. Okay, so the priority that we're going to have is, again, whatever's attached to that carbon that's going to be highest in atomic weight to lowest. So the first is going to be nitrogen, since that's atomic weight of 14. Carbon's going to be 12, so that's going to be second. Third is going to be deuterium, since that's atomic weight of 2. Okay, so first priority is going to be in the back. So in other words, we want to flip things over. But let's just do it as it's depicted here. So we'll have NH2 first, followed by CH3, which is second, followed by D, which is third. Okay, so as we're looking at it, it looks like R, right? So rectus, or right-handed, or clockwise. Okay, now if we were to take a look at, let's say, the model of that, it would look a little bit different, seeing as we would have different connectivity here. Or things would look different. The connectivity would be the same, but we'd have a different sort of perspective about this particular center compound. to try to work as fast as I can here, put it together. Not breaking a nail. Okay. Do it the easy way here too. Make sure I have this just right. Okay, so here we have nitrogen or NH2 or an amine group. We have this white ball, which is supposed to be a representation of hydrogen. This one here, this is a different color. This is going to be D. And then this is going to be CH3. So as depicted, this is what you're going to see. Okay, so now we want to have those highest priorities in the front and this hydrogen in the back. So now if we, and remember I said before that it was looking rectus, so it's going to go 1, 2, 3, or clockwise as it's depicted here in 2 dimensions. Now, if we have it like how I've rotated things, this is going to be 1, 2, 3. Okay, so in other words, even if we turn this around, we're still going to have this particular configuration. Okay, so you can't always rely on just twisting things or saying, oh, hey, it looks like it's R. It's got to be flipped around, since this is in the front. Not necessarily, okay? So you got to pay attention to how things are connected. Again, I think these model kits are really worth their weight in gold, even though they're plastic. But they're really something. They'll really help you out and get you out of a serious bind, especially if you're thinking about Fisher projections and zigzag models and what have you. Okay. So again, highest priority nitrogen, carbon, deuterium, which is just heavy hydrogen, and then hydrogen itself, which is going to be the last. Not always are you going to see hydrogen there as the lowest priority, so bear in mind that you may see a methyl group or even an ethyl group there that's the lowest in priority. Okay. Alrighty. So again, if we were to redraw this, let's say we twisted this however many degrees. So D still stays up there at the top. I usually like to keep that sort of position there and so nothing shifts around too much. Okay, now that hydrogen's in the back, right? So in other words, we've sort of rotated it a little bit. So now we have clearly an R configuration, right? 1, 2, 3. Okay, so that's going to be R. All right, so if we were to swap NH2 and CH3, again, just keep deuterium up at the top. Okay, so these are mirror images of one another. So it's going to go 1, 2, 3, S. Right. So So in other words, they're going to be enantiomers of one another. Okay, so let's go over the next, or why don't you pause for a minute and go into the next space where it says conceptual exercise. What are the configurations for each of the following? So I'll put them up on the board here after the pause, and we'll go over them together. All right, so here are the 3 examples that I included in your notes here. So the way we're looking at it right now, the top priority is in the back, so that's not going to fly. But since we do have a model that I put together, you know, I'm going to let you guys kind of think about this conceptually on your own. Maybe use your own model kit if you have one. Again, I can't stress how important they are and how useful they are in this course. But again, they are totally supplementary. Thing you want to do here is to get this back into that sort of top 3, if you will, is to keep this phenyl group position how it is, but twist and rotate the rest of the molecule, right? Because this is free to rotate. It is 3 dimensions, and it is a single bond there. So, in other words, put that, whoops, wrong color. Where is there we go. Okay, so we've established this is a phenyl ring. So I'm just going to move that. Scratch that off to occupy some, or to free up some space here. Okay, so that ethyl group is going to stick up at the top now. That NH2 group is going to be about the same plane. And now that lowest priority CH3 is going to be sticking in the back. And since we've just rotated that bond that's connecting the stereogenic carbon to the phenyl ring, we're going to leave it as is. Okay, so now we have our top 3 in the top, or in the front, sorry. So this is going to be first, number 1, the nitrogen itself. All right, so we have carbons that are connected to other carbons. The one that's going to be the tiebreaker here is that this carbon about the phenyl ring, or where the junction is connected to technically 3 carbons, even though it's connected to 2. You know, one singly bound, one's going to be doubly bound. So, in other words, this would really sort of branch off like so. Or you can imagine the phenyl ring branching off like so. Again, you're going to have a double bond on C double bond on one end, C single bond on the other. Okay. And then, you know, it's going to branch off of where that carbon is, that stereogenic carbon. So this is going to go first priority, second priority, third priority. Okay, so in other words, it's going to be S for sinister. Okay. All right, the other 2 are a little bit more straightforward, thankfully. We have the OH group, which is going to be highest priority. We'll just go ahead and put that 1 right there. Our other options here are CH3 and then the cyclohexane ring. So since cyclohexane has a junction with 2 carbons attached, it's going to be the tiebreaker. So we'll put that as 2. And we'll put this methyl group up top as 3. And our lowest priority, behold, is in the back. So that is also going to be counterclockwise, or S configured. And the last one is going to be a quaternary carbon. Now we have ethyl here, we have ethyl here, and then we have phenyl. So, and then we have hydrogen in the back. What's the issue? Is that this actually isn't optically active at all. Reason being is because these 2 are identical. So remember that you have to have 4 different coordinates branching off of that stereogenic carbon, or nitrogen as it were, to actually make it stereo specific. Okay, so if you have two things that are identical, whether or not it's in a ring or if it's a part of a linear species, if there are two things that are branching off of it that are identical, that means that they are not stereo specific. All right, so here's a Fisher projection, kind of an ugly looking fishbone looking thing here. Now, notice how you have a top and a bottom substituent, what have you. So it's part of a linear chain. But the thing to pay attention to here is that each one of these junctions you see here is actually a stereo center. So this is not stereo specific, again, because it has two hydrogens attached to it, and then an OH. So then, therefore, you're not going to see another junction here. And then at the top, this is going to be shorthand for an aldehyde. So in other words, it's just going to look like that. Okay. So in other words, it's going to be two-dimensional and it's free to rotate, etc. Okay, so here's the deal. We have three different compounds, or we have all of these compounds which are the same molecular formulae. However, they have different connectivity. Okay, so when you have things that have changed from one side to another, that means you have a different configuration. Well, before we get going and sort of separating these three isomers out, let's figure out how many possible isomers we could have. Now, we have a possibility of two configurations for each particular stereo center. In this particular instance, we have three different stereo centers that that can have those different configurations. So we would take 2 as our base to the whatever power is in our exponent. So the count of different stereo centers is going to be your exponent. So in other words, 2 to the third, so that should be 8 different stereo isomers. Okay. So let's take a look at these, the left and the middle Fisher projection. Now, one other thing before I kind of make my comparison here, sorry if I'm forgetting stuff. If we were to look at this from a sort of linear chain, this zigzag that we've typically looked at linear molecules, not in sort of just a straight line like how you see, is that this would say stick into the plane of the board. This carbon would stick out of the plane of the board. This would stick into the plane of the board, out of the plane of the board, into the plane of the board, right? So, in other words, if we were to do our carbons, let's say this is the, if, let's say my eyeball right here, and I'm looking up, you know, right in the plane of the board, right? I'm looking straight up. I'm looking at this 1, 2, 3, 4, 5 carbon backbone. Okay, I'm going to put this OH right here. So it's going to be sticking down at the bottom. So I'm looking directly at this. This is where I'm at. So this is going to be going into the plane of the page. This is going to be sticking out of the plane of the page, or going towards me, okay? Towards where your eyes are. Okay, so with that said, let's try to figure out where these substituents are going to be sticking off. We're not going to put the actual configuration. We're just going to put where they would go. Okay. Because really what we're looking at here is how are we going to fix everything to where it kind of aligns with Vesper, right? We don't want everything in the same plane because, or sorry, rather we don't want everything to be kind of bundled up because as we've known or as we've seen from the conformers, everything that's kind of built up and sterically bulky. Remember, these things tend to take up a lot of space, even if you do your space filling models or these little models that you have here. Right, all of it adds up. It just gets a little bit clunky, especially when we were looking at that quaternary amine example earlier. Okay, so this is going to matter in terms of zigzag and how things are going to appear. So while they just look two-dimensional from the Fisher projection perspective, you still have to think about, oh, is it sticking out or is it sticking in? Okay, so the best way I like to do it is to make sure that this goes in, and then the first stereogenic carbon is going to stick out. So this is going to go out, in, out. Okay. So it has to, since we're going, so this would go in, out, in, out, in, if your eyeball's right here. Okay. All right. Now, let's just do some comparisons here, and then we'll figure out what each configuration for each stereogenic carbon is. Okay. So we try to make a mirror image here. Do we have a mirror image? Actually, yes, we do, because we have hydrogen sticking on the left side here. We have them sticking into the right side here. We have mirroring substituents, but they're going to be on sort of different ends of where this backbone is. So in other words, these are just going to be hydrogen, so it won't matter. I'm not going to draw a zigzag here, but for each of these, because it would take a little while and I would actually have to put stuff together. But just to keep things in perspective, these are going to be mirror images of one another. The relationship between the center and the right side are going to be a little bit different. Notice how the configurations for the top two stereogenic carbons are going to be the same, but there's an inversion here on the third one, or let's say carbon number 4, as it were. Okay, so in other words, if there's one change in the stereogenic carbon configuration, then that means these are going to be diastereomers. These are going to be enantiomers because everything has been flipped over. Okay? So, these are going to be enantiomers. So let me erase this real quick. Okay, so mirror images of one another. And then this one and this one are going to be diastereomers. Again, because there's just a change in one stereocenter. Okay. What's the difference between these two? Well, they have two stereogenic carbons swapped out in terms of configuration. So these two will be diastereomers of one another. Okay? All right. So, now, with what I've said, why don't you pause this for a couple minutes and see what you get for your R and S configurations. Now, think about what I did before when I was talking about, R and then flipping it over to S because things weren't where they needed to be spatially, right? So, in other words, if something's lowest priority and it's in the front, it needs to get flipped over and reverted to the back. Okay. So pause for a minute and give this one a go before we get going. So we're going to just look at this particular isomer, and we're going to figure out what the configurations for carbons 2, 3, and 4 are, and then we're just going to figure it out for the rest of these. Okay. All right, so we have OH, which is going to be first priority, right, because we don't have any other oxygens bound to this stereogenic carbon. So that's going to be 1, followed by 2, because if we have an aldehyde right here, remember we have 2 CO single bonds. So that's going to beat out CO, CH, CC, right? Because oxygen is going to be highest priority. So this is going to be the next for the tiebreaker, and then third here at the bottom. Okay, so what does that mean? As we're looking at it, it looks as though things are going to be S. But remember that if this stereogenic carbon is sticking out, that means that these, it's sort of the bow tie thing that your text talks about. So the OH is going to be sticking out as well as the hydrogen. So that means that if it's sticking out, that means you need to flip this around. So if it's going to get flipped around, that means that that highest priority is going to go on to the other side. So in other words, as we're seeing it, it looks like it's R, but actually it's going to be S. So R, in quotation marks, to S. Okay. So that's for carbon number 2. For carbon number 3, this is going to be, again, first priority, this OH. Okay. Second priority is going to be up at the top. Again, because that's going to beat out. So you have an oxygen directly attached here. You just have a methyl group attached here and another methylene group. You have a methyl group, or sorry, you have a OH group here, and then you have an aldehyde. So in other words, this is going to be second priority about the third carbon. Okay, so 1, 2, 3. We don't need to flip anything this time because this is going into the plane of the page. So in other words, this should go 1, 2, 3, which is going to be S. Okay, and last one. Okay, so we have, so this is going to go out, in, out. Okay, so once again, that hydrogen's going to be lowest priority, but it's sticking out of the plane of the page, so we need to put it the other way. So let's remember that, try to figure out what our configuration is as we see it, and flip it around. Okay, so highest priority is going to be this carbon here, because you have OH attached to it. This also has OH attached, but the tiebreaker is this next carbon. Okay, so in other words, this is going to be number 1. This is going to be number 2, and then methyl is going to be number 3. Okay, so in other words, as it appears, it's going to go 1, 2, 3. So that is S. We'll put that in quotation marks again, because we need to flip that and put it into the plane of the page, not out of the plane of the page like we assume it is. Okay, so in other words, it's going to be R. So it's going to go S, S, R for these configurations. Okay, so if we had an enantiomer of an SSR configured stereoisomer, now we're going to have R, R, S. See how easy that was? So all you have to do is just flip each one of the stereogenic centers, or carbons, whatever. Okay. Now, so this is going to be quick for the third one as well. If we have 2 of the same stereogenic carbons at the top, or at least with carbons 2 and 3 here. So the only thing that's flipped over is this carbon number 4. So in other words, if it's S right here, it flipped over in configuration. That means it's got to be R over here. So R, 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 like a seal. Okay? All right, so here's a few nomenclature examples to get you guys sort of practice here. So we have a few different stereo centers here for the first one. Excuse me. Okay, the first being this particular carbon here, stereogenic. Okay, and then we have an alkene that's tetrasubstituted with all different substituents about it. So in other words, we can't ignore the stereochemistry of either of these parts of the molecule. Okay, so let's try to count the largest carbon count. So that's really kind of instrumental or basic here with in terms of nomenclature. So we're going to go 1, 2, 3, 4, 5, 6, 7. That's going to be the longest carbon chain. So we'll put heptene, right? So we start from this end. It should be 1, 2, 3, ene. We start from this end. It would be 4 ene. So we want to go from left to right here. So hept 3 ene for our root. Okay. Now we have a methyl, we have a nitro, we have an ethyl, we have a fluoro, all branching off of that main chain. Okay, so we'll just put the numbering scheme here. 1, 2, 3, 4, 5, 6, 7, whatever. Okay. So we'll have a 3 ethyl, 2 methyl, 1 nitro, 4 fluoro. We have to put all that in alphabetical order. So let's give it a whirl here. We'll have 3 ethyl, 4 fluoro, 2 methyl, 1 nitro. Okay. And then, okay, so that takes care of all of the branching groups. Okay, so let's figure out next what the stereo center is here. So we have CH2 here, which is attached to a nitrogen. We have C, C, C. Okay, so carbon and a carbon. Nitro group is going to beat all that out, right? Everything here that's beyond that particular carbon, that quaternary carbon. So we will treat it as first priority here. Okay, second priority because this is going to beat out a methyl group, right? And third priority at the top, and assuming there's a little hydrogen sticking there in the back. So it's going to go 1, 2, 3. So it's going to be S configured. So it's going to be S. We'll put that in parentheses, this beginning. And since we only have one ene or alkene, we don't have to put a locator for the whether it's E or Z. We've already put the locator number in terms of the ene on the root. So we're good on that. Okay, so we have 3 and 4 positions here. So the higher priority is going to be what's here for this particular carbon, and then what's here for this particular carbon. So fluoro is going to beat out carbon, right? And then this branched carbon is going to beat out this ethyl group. So in other words, this is going to be Z. So it should be SZ hyphen 3 ethyl, 3 hyphen ethyl hyphen 4 hyphen fluoro hyphen 2 hyphen methyl hyphen 1 hyphen nitro hept hyphen 3 hyphen ene. There you go. Okay, next one should be a little bit more straightforward. Okay, so we have longest contiguous carbon chain here, which is going to be 1, 2, 3, 4, 5, 6, 7, 8. So oct, ene, ine. So oct, diene, right? So we have 1, 2, 3, 4, 5, 6. So 1, 6 diene. What was that? 1, 2, 3, 4 ine. Ooh, so that's the main root. Okay, so we have trans here. This is just vinyl, so it doesn't have any stereospecificity to it. So we'll just put this as either trans or E. So we'll put E. And we really only have that one methyl group to account for in terms of branching, because everything else is part of a chain there. It's somewhat linear. Okay, so put that E for opposite. So let's see, 1, 2, 3, so it's going to be 3 methyl. Okay, and then what is this going to be? So this is going to be first priority, because you can imagine this triple bond CC barrel that you see right here. This is going to be C, C, C versus C, H, C, and then CH3. So it's going to be lowest priority. So it should go 1, 2, 3, which is going to be R. So in parentheses R, comma, E, and parentheses hyphen 3 hyphen methyl oct hyphen 1 comma 6 hyphen diene hyphen 4 hyphen YNE. Sounded like a robot saying that. Okay, so that is the nomenclature. This is the nomenclature for the first one. Whoops, I need to cross all that out. Let's look at this bottom left example here. Okay. So the longest running chain here is going to be 1, 2, 3, 4, 5, 6. Is that the way we should count it? Remember, we want to have this be the low. If we have unsaturation here, we want it to have the lowest locator number. So in other words, we should go 1, 2, 3, 4, 5, 6. Okay, so it's going to be hex. Like I put a hex on you. 2 YNE. Okay. All right, so we have a bromo group. We have 3 methyl groups hanging off, so we could have a trimethyl, right? So we'll say that's a 4 bromo, 4, 5, 5 tribromo, 4 comma 5 comma 5 trimethyl. Okay, hex 2 ine. But we do have one stereocenter here, so we have to account for that. So bromo is going to be in the front, very good. So it's going to be highest priority by a long shot. Then we're going to have this carbon directly attached to 3 carbons, so to speak, right? So this carbon is attached to 3 carbons as well. but they all dead end in hydrogens. There's a continuation with this carbon here. So in other words, this carbon right here is going to be your tiebreaker. So in other words, this is going to be first priority, this is going to be second priority, and this is going to be third priority. Okay? And then that methyl in the last, so whatever. It's just sticking in the back, we don't care. So 1, 2, 3, so that's going to be S. Okay, so S, 4-bromo, 4,5,5 trimethyl hex 2-YNE. All right. Last one, here's the Fischer projection. Notice that not all those junctions are actually stereospecific. So hint, hint. Another thing you want to pay attention to if you see something like this is that you see some, look to see if there's some kind of axis symmetry here, or plane of symmetry rather. You're not going to see that because you have a bromine at the top here and then a chloro at the bottom. But here's the trick to try to figure out what kind of numbering scheme you can have to make everything look like it's, you know, in the right order. Well, if we're going with the longest contiguous carbon chain, we could go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. But here's the thing: is that if we choose these as our main root, you know, chain, if you will, then what that's going to do is basically we're going to have something at the 2 and 4 position, right? Now, if we had this, this would be at the 1 and 5. So, in other words, we could have, you know, bromo, methyl, chloromethyl, branching off of, you know, 2 and 4 respectively. So how we would do that is, let's just say this is going to be 1, this is going to be 2, this is going to be 3, this is going to be 4, this is going to be 5. Okay, so remember we're also giving this the lowest locator numbers because these two are stereogenic carbons. 3 is not, so bear in mind that. Okay, so we're just going to go with 1, 2, 3, 4, 5, so it's going to be pentane as the root. We don't have any unsaturation here, so it's going to be just regular old pentane with things branched off of it. Okay, so we have 2 bromo methyl, 4 bromochloro, 4. Remember to put that in parentheses, the chloro methyl. Okay. So 2 bromomethyl, 4 chloromethyl pentane. Okay. Now the only thing we have left here is the stereogenic carbons and figuring out their configuration. Okay. So if we're just looking at everything here, we have a tiebreaker, which is clearly right here. So that's going to be number 1. Number 2 is going to be right here because this dead ends at a hydrogen. Okay, so that's going to be number 3. So as we're looking at it, it looks like S, but remember that this first one is going to wedge out. So this is going to wedge out and this is going to wedge out. So in other words, whatever we're seeing needs to get flipped over. So this is going to be 1, this is going to be 2, this is going to be 3. As we're looking at it, it's going to be S, but S in parentheses or in quotation marks goes to R. Okay, so this is not a stereogenic carbon because you have 2 hydrogens attached to it, and remember you need a total of 4 different coordinates. Okay, so now that we have the bottom one just to worry about, we're going to have highest priority with the chloro groups attached, second highest priority at the top, and then third highest priority in the methyl. Of course, the hydrogen is going to be fourth. Again, remember this is going to go out, in, out per the Westerber model. So if this is going to be sticking out, then that means that this hydrogen needs to get twirled around to the back. Okay, so when you twirl it around to the back, it's going to go 1, 2, 3. As we're looking at it, it's going to be R, but if it were flipped around, it's going to be S. So we'll put R in quotation marks, turn it around to S to be what it actually is. So it should be 2R, 4S, dash, or sorry, hyphen 2 hyphen parentheses bromomethyl end parentheses hyphen 4 hyphen parentheses chloromethyl end parentheses pentane. All right. So take a look at some of the practice problems that I have following that little exercise that I just went over with you, and check in during office hours and we can go over them together. Thanks everyone. Have a great day.